I have already told you the answer. I gave you the answer. What did I say? You should write the formula of the Fourier transform of your new signal, which is x of t minus 1. So let's write the Fourier transform. This is the Fourier transform. All you need to do is to apply a change of variables to this t minus 1. Let's call it t prime. As t ranges from minus infinity to infinity, t prime also ranges from minus infinity to infinity. It's just a shift, so the integration limits don't change. X of t prime is what you write. Now, if t minus 1 is t prime, what is t then? That is t prime plus 1, isn't it? And dt is dt prime plus 1, you may say, but the differential doesn't change. The derivative of t and the derivative of t minus 1, which is t prime, are the same. So you can safely write a dt prime here instead of a dt. And the integration limits don't change either. What you come up with is the integral x of t prime e to the minus j omega t prime and e to the minus j omega dt prime. You need to take this out of the integration because it has nothing to do with t or t prime. And you have a plain integral formula e to the minus j omega t prime dt prime, where this part obviously corresponds to x of j omega. Therefore, the overall thing is e to the minus j omega x of j omega. That is the expression of y of j omega, which is one shifted version of the original x in terms of the original x of j omega, which is the Fourier transform of x of t. So this shows us one important property, and today we will start with listing out properties of Fourier transforms. Usually we will solve the questions using such properties. And the property is saying that if you apply a shift to your signal, then you multiply your Fourier transform by a complex exponential. As a matter of fact, that complex exponential is related with the amount of shift as follows. So let's call it like properties of Fourier transform, which are extremely important, right? Without these properties, it would be extremely difficult to solve questions just by taking the integrals and applying Fourier transform formula. The first property is this. If x of t has a Fourier transform x of j omega, then x of t minus t0, this t0 could be positive or negative, it doesn't really matter, has a Fourier transform of e to the minus j omega t0 x of j omega. So in the question, this t0 was 1, therefore we had e to the minus j omega times x j omega. Okay. And the proof was already there. Just you need to apply an amount of t0, a shift amount of t0, and by changing the variables inside the integration, you will easily find or obtain this. These properties that I will list, of course, are not very difficult to show. They are indeed as easy as these ones. They are very easy to show. But you need to know them, and you need to develop skills to use them. Without using such properties, it's, as I say, quite difficult to solve any question. Sorry. So this is, what can we say? as a name to this time shift property. Linearity is an obvious property of Fourier transform. That is, if x of t has a Fourier transform x of j omega and y of t, another signal, has Fourier transform y of j omega, then a times xt plus b times yt has the combination, the linear combination of these two signals has a Fourier transform ax j omega plus b y j omega. Quite simple. And that thing comes again from this kind of a Fourier transform integral formula. Inside the signal place, you just write two components, and those two components, since this is an integral, integration is a linear operator, can be split into two separate integrals. The first separate integral will produce xj omega, the second integral will produce yj omega. And if you scale your signal by a, the overall integral will also be scaled. As I say, integration is a linear operator, just like derivative or differentiation. Now, let's start seeing examples where we can use, for example, time shift and linearity properties. And here's the question. One, two, three, four. On the time axis, this has a level of 1, this has a level of 1.5, let's assume. So this is our shape of x of t. And we want to take the Fourier transform of it. It's not very difficult to evaluate the Fourier transform even for this signal, because you take the integral, and the integral is 1 from 1 to 2, or the signal is 1 from 1 to 2. The signal is 1.5 from 2 to 3, and then it's equal to, again, 1. The signal is 1 from 3 to 4. And all other integration limits will produce nothing because the signal is 0. So how do we attack? You can attack it like this if you don't have any of these properties, or if you don't want to use them. But it may be a better idea to think of a separate signal x1 of t, that is a normal rectangular pulse train from minus 0.5 to 0.5 with a magnitude 1, and that is the sinc function generating signal that we already have. And the other one, let's call it x2 of t. That's a wider version of it, from minus 1.5 to 1.5 with a level of 1. Indeed, we have solved this problem for a generic, an arbitrary value of t1. From minus t1 to t1, we already have the solution. So let's write down the Fourier transforms of these things. The first one has a Fourier transform of 2 sine omega over 2 over omega, or sine omega over 2 over omega over 2, which is the simplest sinc function that we can think of. For the other one, it is 2 sine 3 omega over 2 over omega. These two. Now the first one, if you just combine as they are, as you see, will make the top portion to reach to a value of 2. So this must be scaled by 0.5 and then added to the other one. In fact, I'm trying to get a third signal, x3 of t, to be equal to 0.5 times x1 of t plus x2 of t, which reproduces this shape in the center, symmetric center. Of course, it's not the signal that we are looking for. Our x of t is shifted towards right version of x3. So what is that? X of t is equal to, and how much shift does it correspond to? 2.5, right? x3 t minus 2.5. That is our signal. So we need to apply the linearity property first. If this has a Fourier transform of that and this has a Fourier transform of that, something times this plus this one will have the Fourier transform that something times this plus this, which is the linearity property. And then we will combine them. Afterwards we will apply some amount of shift, 2.5 shift. So what's the overall thing? What's the overall expression that we get? That is x of j omega is equal to e to the minus j omega times 2.5. That much shift is applied to the overall thing, and then I'll open a large parenthesis. Inside this parenthesis I have two expressions. One of them is half of the first, which is sine omega over 2 over omega. The other one has the same over omega expression, so let me put a larger ratio here. 2 sine 3 omega over 2 over omega. You can safely say that this is the answer and you are finished. You may try to further simplify it if it is simplifiable. I don't know. I didn't try, and that's not necessary for this example. So we are finished. Otherwise, as you see, if you apply three separate, well, that's also a possibility. There is another way to attack the same problem. You may say that this is a rectangle, the other one is another rectangle, and the third one is another rectangle. And they are all generated from this term. Shifted by 1.5, then by 2.5, and then by 3.5, and the one in between is scaled by 1.5. It may have three components generated like that. That's also possible. It may be a good exercise to show that the result generated like that would be equal to this. But it will take some time to show it. It's not necessary. You can give that answer or this answer, and you may say that they are the same. They are equal, and both of the answers would be correct. Now, another property, let's start another property. That is conjugation and symmetry property. This conjugation and symmetry property, or such properties, are generally valid for complex signals. For non-complex signals, or for real signals, in other words, you can specify such properties for obtaining some certain properties of Fourier transforms of real signals. And the property is as follows. If x of t has a Fourier transform of x of j omega, then what is the Fourier transform of x conjugate of t? And it's not very difficult, like all the other properties that we will see. It's very easy to show this. Or I could ask you this as a quiz question or as an exam question. What is the, or express the Fourier transform of x conjugate of t in terms of x of j omega, which is the Fourier transform of the normal x of t. What you do is just put this inside the formula, and then take the conjugates of the whole term, and in the complex exponential, the conjugation will make e to the minus j omega t to become e to the plus j omega t. So something is disturbed in the expression, then you need to change or replace omega by minus omega. Replace that or make that kind of a replacement or substitution. And in fact, that's it. That's all. You first take the Fourier transform expression overall, and then you negate the once again the frequency parameter omega. So this will be the Fourier transform of x conjugate of t. The Fourier transform is x conjugate of minus j omega. Now, for real signals, since x of t and x conjugate of t are the same, these two must be the same as well. X of j omega is equal to x conjugate of minus j omega. Or if you wish, you may remember this more easily like this. Take the conjugates of both sides of the equation and you say x conjugate of j omega is equal to x of minus j omega. What does this tell us? It is saying that, it is telling us that if you conjugate a Fourier transform expression, what were the Fourier transform expressions that we have already? They were mostly real, but for example, let's assume this example where it is not real. We have e to the minus j omega thing, some portion. So it is complex. X of j omega is this. For a real signal's Fourier transform, it is always valid that when you take the conjugate of this expression, what is the conjugate of that? It is e to the plus j omega 2.5 times something real. That is the conjugate. And that is the same as replacing omega with a minus omega. It looks quite safe to say it just by looking at here, because this omega is replaced by minus omega, and it becomes therefore e to the plus j omega. But the right hand side is also disturbed here, and we have a sign here and another sign here. If you put a minus omega, sign of minus omega is minus sign of that thing. Same here. Sine of 3 omega, when you negate the omega, it becomes minus. So the numerator will become a negative thing, expression. But the denominator will also be negated because omega is replaced by minus omega. So those two negatives will cancel each other at the top and the bottom, and you will come up with the same expression. That's not a coincidence. That is a necessary property for the Fourier transforms of real signals. So always check this out. You have to check this whether the conjugate is really corresponding to x of minus j omega as it is, without any further alterations. Sorry. Now, the symmetry, this is about conjugation part. We have covered the conjugation part. Now let's cover the symmetry part, or you may think of it as a separate or a different property if you wish. Is like this. If your signal is symmetric, by the way to obtain a symmetric signal from any signal is by taking the even part of it. So the even part of any signal is automatically symmetric, and a symmetric sequence will always be symmetric and real. No, it doesn't have to be real, sorry. It's just a symmetric sequence will always obtain or will always result in a real Fourier transform. I have mentioned about this in the Fourier series properties. We said that the Fourier series coefficients of cosine was 1 over 2 and 1 over 2, which is real. Whereas, for example, the Fourier series coefficients of a sine were 1 over 2j and minus 1 over 2j, which is imaginary. So, if your signal is symmetric, you come up with a real Fourier transform. And the even part of any x of t will result in the real part of the x of j omega expression, the Fourier transform. So let's consider this problem again. Can you find the even part of this signal? I'm easily writing EV. EV of x of t. Can you find it? The method to find an even function or find the even part of a function is quite simple. That is x of t plus x of minus t over 2. This is the even part of any signal. So all you have to do is take that signal, find x of minus t, which is by flipping around the 0 axis, and sum them up. It will contain two components. The energies must be normalized by dividing by 2. And it becomes a symmetric signal. That symmetric signal will have the real part of the Fourier transform of that. So what you really need to do, if you come up with any signal like that with two portions at the left and right, then the Fourier transform of that will correspond to the real part of this large expression. And can you find the real part of this large expression? Yes, of course you can. You need to expand this thing using the Euler's expansion with a cosine and sine term. The cosine term is real, sine term is j times something. So forget about that j times something because it's multiplying something real. That cosine thing times this large parentheses will correspond to the real part of x of j omega for that example. So it's just think of the cosine if you forget about this property. If it is symmetric, then the Fourier transform is real because the Fourier transform of a cosine is real. And the other counterpart is the odd part of x of t. And how do you find the odd part? That's simply x of t minus x of minus t over 2. So what you do is you flip around the shape and then negate. So it will be completely antisymmetric. An odd signal is completely antisymmetric. And what is the Fourier transform of that? What does it correspond to? It corresponds to the purely imaginary part. And in the imaginary sense. So it is j times the imaginary part of x of j omega. So for such signals, for such antisymmetric signals, the Fourier transform is only in terms of j, and there is no real part of it. It is purely imaginary. And think of the sign. What was it? It was 1 over 2j and minus 1 over 2j. 1 over 2j is minus j over 2. Minus 1 over 2j is plus j over 2. So it is in the j parentheses. It can be put in a j parentheses. There is nothing real in the Fourier transform of a sign. And that is a valid property for every antisymmetric signal or for every odd signal. If you have such an odd signal like this or like that generated from our previous example, then again you need to expand this part using the Euler's formula and take only the sine part, and j times sine, that thing, times this large parenthesis will correspond to the Fourier transform of the odd function generated from our example. Okay. Now let's attempt to use these properties in an example. By the way, this example, while solving this example, you don't really need to use these properties. So you can find it in an alternative way if you wish, but just verify that these two are the same. So what am I talking about? Well, we will do in both ways in a way. The new example is an exponential. It's a real exponential. E to the minus a absolute value of t. and a is positive, so that it decays. First of all, you must visualize in your head how this looks like. What does it look like? It's a decaying exponential towards the right because a is positive, and it is also a decaying exponential towards the left because of this magnitude operation. Okay, there is no minus t in the exponent. So it's a two-sided decaying exponential that this thing corresponds to. And how can we attack that problem? First, let's attack it without knowing anything. That is the formula. We must split this x of t into two parts. For one of the part, it is from minus infinity to 0, where absolute value of t corresponds to minus t. And therefore we have e to the minus a times minus t, which is at, right? And e to the minus j omega t dt plus, from 0 to infinity, absolute value of t is itself, t. Therefore we have e to the minus a t, e to the minus j omega t dt. Then we will combine these two expressions. The first expression, if you put into a parenthesis of t, it is e to the, in t parentheses, a minus j omega. And that's an exponential term, a minus j omega. That appears as 1 over a minus j omega e to the t parentheses a minus j omega from 0 to minus infinity, right? That's how we integrate. Now I am not going to spend any time on that, and you must just trust me, and if you don't, just check it out. From 0 to minus infinity, if you evaluate these parts, the first part will be 1, the second part will be 0, so we only have this 1 over a minus j omega as this integral, this first integral. And over here it will be in an e to the minus t parentheses a plus j omega, so there will be a minus 1 over minus a plus j omega, and there will be a minus sign here. But after the evaluation from infinity to 0, it will be 0 and plus 1 in the two limits, so there will be another negation, and this minus will be cancelled. Nevertheless, the overall integral that we will have will be this, the summation of these two terms only. That's calculus integration. And if you further simplify it, it will be 2a over a squared plus omega squared. Now this is, by the way, quite a nice example of a low pass signal. What was the Fourier transform of e to the minus at u of t? That is half of this function. What was the Fourier transform of that? Do you remember? What is the Fourier transform of this? The right hand side. 1 over a plus j omega. This was the Fourier transform. Now, interestingly, this new signal that we have is the even part of the signal. Let's call this thing as y of t. So the argument is x of t is the even part of y of t. Because what was the even part formula? It was this signal, which is this. Flip it around and add them up and divide by 2. That is precisely that signal, except for the fact that since it is divided by 2, we must multiply the even part by 2. So it is twice the even part of y of t. It's not only the even part, but it's twice the even part. Now, starting from there, what do we need to do for the Fourier transform of this, which is y of j omega? What is x of j omega then? It is twice the real part of y of j omega. Isn't it? Since the even part is taken in the signal, the real part must be taken in the transform. That's what it corresponds to. What is the real part of this? The real part of that is, well, let's write it first. Twice the real part of 1 over a plus j omega. Since this is in the denominator, we must multiply the the conjugate of the denominator at both sides. It's twice the real part of, what's the conjugate of a plus j omega? It's a minus j omega. A minus j omega over a minus j omega, a plus j omega. I am multiplying both the numerator and the denominator by a minus j omega. It's twice the real part of a minus j omega divided by, so since we are multiplying with the conjugate, it becomes a real signal, which is a squared plus omega squared. That's how we make the denominator real, because I want to get a complex value in the numerator. That's how I can separate the real part and the imaginary part. From the denominator, I cannot separate the real and the imaginary parts. So this is it. And from the by the real part, this j omega portion is gone, and it is 2 times a over a squared plus omega squared, which is this, the same. So you can solve the question like that as well. It's just a verification. Under some circumstances, this may be easier to attack. This may be an easy way to make your attack to the problem, to the solution of the problem. In some other cases, of course, if you cannot think of any properties, if nothing comes to your mind, then obviously you are stuck with the situation of this formula, and you must just apply the formula and try to get a solution. In the examinations, unfortunately, you have limited time, so it may not be a good idea to do it like this. First, try to solve the puzzle and try to represent your signal in terms of the properties that we already know. That would be highly recommended. For today, the last property, the properties won't be finished at this point, but I will proceed as much as possible as the time permits. It's differentiation and integration. Well, we already know this property, sort of. If x of t has a Fourier transform of x of j omega, when you take the derivative of that, can you guess what the Fourier transform will correspond to in terms of x of j omega? Do you remember what was happening to the Fourier series coefficients? That was the integral. It's just the opposite. It was j omega. So we were multiplying by j omega, and omega is k times omega 0. So it was j times k times omega 0 times ak. That's what was happening to the Fourier series coefficient. But now it's even easier than that. It is simply j omega times x of j omega. So when you have a derivative signal like this, and if you know the Fourier transform of the non-differentiated version, this one, then just multiply it by j omega and you come up with the derivative version. Now, there are several insightful properties that the books don't necessarily mention, but I'll try to motivate them as much as possible. For example, if this signal has some DC bias, if it is above the DC level and making a variation. For example, if it is A plus cosine omega t, or cosine some certain omega 0 t, A plus. When you take the derivative of that, that A will cancel, okay? So the derivative of a signal will have no DC. The DC value will be 0. What is a DC value? A DC value is the Fourier transform at omega is equal to 0, because that is corresponding to 0 frequency, that is DC. When omega is equal to 0, whatever this value is, it shows you the DC value of your time signal. Now, what happens now? I'm multiplying it with j omega. So suppose that there is a DC value at omega is equal to 0, which is, let's say, 6. This is 6 previously, the DC value, at omega is equal to 0. As you see, at omega is equal to 0, you must multiply it by 0. And the new DC value of this one is always, certainly, 0. Right? That's a very nice observation, and it somehow verifies the necessity of this. You must multiply it by omega so that the derivative will have no DC. This will be 0 at omega is equal to 0, always. But that's also a problem in the inverse operation. When you integrate your signal, which is when you accumulate your signal, what is the Fourier transform of that with respect to the original x of j omega? It is, of course, 1 over j omega x of j omega. But a DC term, a plus c term from the integration, in other words. You remember that plus c? That plus c term is also necessary. And that necessary plus c term comes from the DC value of the original x, like this. Pi times capital X of 0, which is capital X of j omega at omega is equal to 0, times delta omega. We are inserting a deliberate DC component, in other words, into the system. This is usually forgotten, and it doesn't really change the figure much. Okay? Because the shape, that's just a single impulse at the DC, nothing else. This is an impulse at the DC. The other term describes the shape of the integrals Fourier transform at all places of omega, at all values of the frequency. Now, I'm not going to solve these, but I'm going to write example questions like that. For example, we said delta t has a Fourier transform of 1. That was one of the first examples that we solved. Then what is the Fourier transform of u of t? We'll talk about this, because u of t is the integral of delta t. Or conversely, delta t is the derivative of u of t. So these two have inverse derivative versus integral relations among each other. And what other types of questions? For example, suppose that you have this kind of a periodic signal. What is this is x of t. The question is, what is x of j omega? What's the Fourier transform of that? And we have already solved this using the Fourier series coefficients, and we said that this is the derivative of such a periodic pulse train, right? Because over here the derivative is an upward going arrow. Over here the derivative is a downward going arrow. Over here the derivative is an upward going arrow. So the relation between the two, for example, will also correspond to a similar relation. So this was example 1. This is example 2. A simpler version of the example 2 is example 3, and that is just the Fourier transform of this box. What is x of j omega? We already know it. It's a sinc shape, right? We have found it. It was the very first example that we did. Sorry, it was the second example that we did. But now, solve this thing from this impulse and this impulse, and take the integral of that. Why? Because when you integrate, this upward going will cause this, and this downward going arrow will cause a jump towards the bottom. And these two impulses, are their Fourier transforms simple? Are they easy to take the Fourier transform? Yes, because we know that the Fourier transform of an impulse in the center is 1. So what you need to do is apply a shift, and when you apply a shift, you multiply with a complex exponential. Similarly, when you apply a shift, you multiply with another complex exponential, but this time it's negative, so multiply the Fourier transform by -1. So you come up with the Fourier transform of this expression very, very easily. In fact, it is easier than the Fourier transform evaluation here. These Fourier transforms are easier than that. Just do it and then apply this formula. 1 over j omega times this. By the way, the Fourier transform of such a thing will correspond to a sine. And you divide a sine omega by omega. What was sine omega over omega? Sinc. That's why the Fourier transform of this thing is a sinc. They will be verified. I'm not going to do it now because we don't have time, but next week we're going to do that. Okay, we'll continue with the examples and other properties as well.